All right, in this lesson we'll talk some more about motion along a line, also known as rectilinear motion, linear motion, motion along a line, okay? And again, when we talk about motion along a line, we're typically talking about a line that'll be oriented horizontally or perhaps vertically, okay? So reading through, if f is a function such that s equals f of t, so often x of t is used to give the position on a number line, and a particle is moving along a straight line such that s is the number of units in directed distance of a particle from a fixed point on a line at time t units, then the instantaneous velocity at time t is v of t, where v of t equals f prime of t, or v of t equals s prime of t, which is equal to ds dt. So let's wrap all that up together. Look, sometimes for the position function, as we perhaps have seen, we're going to see x of t, we're going to see y of t, or we're going to see this generic s of t, okay? If it's x of t notation to represent the position, it's going to be horizontal. X is left and right. You'd be dealing with some sort of horizontal line. If it's y of t, we would assume that the line is vertical, because y is up and down. If it's s of t, that's, again, just kind of a generic way of representing a position function in this course, and you'll be told whether it's horizontal or vertical in that case, okay? And all this is saying is, look, suppose you have some position function, then velocity is the first derivative of that position function, okay? So if we're using s of t notation, velocity is the first derivative of s, and we could also write that then as ds over dt if we wanted to, okay? So velocity is the derivative of position, okay? In part A down here, it says if velocity is positive, then the particle is moving to the right, okay? So these notes are assuming you have horizontal movement, but it could also apply to vertical, so let's throw the word up in there as well. When velocity is positive, the particle is moving up or to the right, and it says in the parentheses there that s is increasing. This is just an application of first derivatives, right? If the first derivative of some function is positive, that tells us that the function itself is increasing, okay? And that's what's going on here. If velocity is the first derivative of position, then if velocity is positive, the position function is increasing. And what does it mean to be increasing? Well, think about numbers on a number line. You know, typically the numbers get bigger when we go to the right or when we go up. That's what it means for position to be increasing, right? We're going in the direction where the numbers themselves are getting bigger, and so that gives us direction of movement, okay? So if velocity is positive, we're moving in the positive direction, either to the right or up, okay? That's what that part A is getting at. In part B, if velocity is negative, the opposite, the particle is moving in the negative direction, which indicates either to the left or down, okay? And if velocity equals 0, then the particle is instantaneously at rest. We're not moving, okay? We're perhaps changing direction, or we're just stopped, okay? Just be careful if v of t changes signs, okay, then the particle is changing directions. Okay, and try to understand why velocity is the derivative of position. I mean, if we're measuring position in, say, meters, you know, we might have a velocity that's like, you know, in meters per second. It's the rate of change of your position, okay, and that's your velocity. All right. Down below now, the speed of a particle at any time is defined as the absolute value of velocity. Okay, speed indicates how fast the particle is moving. Velocity also indicates the direction of travel. Okay, so like if the velocity perhaps equaled -2 meters per second, the speed would be 2 meters per second, and we would be traveling in the negative direction, either left or down. Okay. The instantaneous rate of change of velocity is the acceleration. If we look at the derivative of velocity, we get acceleration. Okay, if we take the derivative of velocity, we might get something like -2 meters per second, or per second squared, meaning that every single second the velocity is going down by 2 meters per second. Okay, so maybe at 1 second I'm traveling at -10 meters per second, or 10 meters per second, and then like the next second I'm only traveling 8 meters per second, and then the next second I'm traveling at only 6 meters per second. Okay, the velocity, the rate of change of velocity is changing. That's acceleration. Okay, so the big things to kind of put together here is the position is like your initial function. F is kind of like, you know, if you want to use f prime and f double prime, f is like your position, first derivative is your velocity, second derivative is your acceleration. But we typically use either s of t, x of t, or y of t for position. We almost always use v of t for velocity, and we almost always use a of t for acceleration. Okay, so down here to continue with the notes, acceleration is the first derivative of velocity, which again is the second derivative of position. If acceleration is positive, then the function it came from, velocity, is increasing. Okay, it's kind of like the way f and f prime work. If a function is increasing, its derivative is going to be positive. All right. Next up, if acceleration is negative, then the function it came from, velocity, is decreasing. And finally, if acceleration is 0, then the velocity is constant. There's no change in velocity. And since speed is the absolute value of velocity, we have the following. If velocity and acceleration have the same sign, then speed is increasing. If velocity and acceleration have opposite signs, then speed is decreasing. Okay, let's try to understand that. Okay. You know, it's kind of intuitive in one direction and not so intuitive in the other. Okay. So let's go through and see why this works. Like, for example, if I'm moving to the right and I have a positive acceleration, I'm speeding up. I'm going to go to the right faster. But if I have a negative velocity, if I'm moving to the left and I have a positive acceleration, I'm actually going to be slowing down. All right, so it's not all that intuitive. Let's try to make sense out of why this is the case, okay? But at the end of the day, the important thing is if you're looking to determine when speed is increasing or decreasing, you have to compare the signs of velocity and acceleration over the intervals, okay? But let's assume both positive, acceleration positive and velocity positive, okay? What does that mean? Well, if acceleration is positive, that means that velocity is increasing. So let's make a little thing here. We're going to have some velocity values, and then we'll take the absolute value of those, and that'll be the speed, okay? So I have positive velocities that are getting bigger. They're increasing. So I'll go 1, 2, 3, 4. So speed is the absolute value of those, 1, 2, 3, 4. Notice that as the velocity goes up, so did the speed, okay? When both of these were positive, speed is certainly increasing, right? 1, 2, 3, 4, those numbers got bigger. All right. Let's look at what happens when they're both negative. Same sign, they're both negative. Well, if acceleration's negative, that means velocity is actually decreasing. So I have negative velocity values that are getting smaller. Let's go -1, -2, -3, -4. Notice velocity is decreasing and they're negative, but what happens when I take the absolute value of those numbers? They go bigger and bigger. They are increasing. So we just saw that when velocity and acceleration have the same sign, speed actually increases, okay? What happens now when they have opposite signs? Oops, erase that. The claim is that the speed is going to be decreasing. So let's say negative acceleration, positive velocity. Negative acceleration means the velocity is decreasing. So I have positive values that are getting smaller. 4, 3, 2, 1. Positive numbers that are decreasing, when I take the absolute value of them, they get smaller as well. Opposite sign, speed decreasing. And finally, let's look at when acceleration is positive and velocity is negative. Again, the claim is that speed will be decreasing. Here, acceleration positive tells us velocity is increasing. So I have negative numbers that are getting bigger. -4, -3, -2, -1. Those are increasing in value, but they're still negative. What happens when I take the absolute value? Certainly those values are decreasing. 4, 3, 2, 1. Okay, so the idea is to determine, again, when speed is increasing or decreasing, we have to compare the signs of velocity and acceleration, okay? And so let's do some problems. Down here, the thing that I crossed out is some information about gravity. We don't really need to get into that in this course, okay? You can read it if you want. Nothing you're going to see either from me or on the AP exam. Okay, so we're going to do these examples together, okay, and then the homework is to do these problems. And you can certainly use your calculators, you know, to help you out finding zeros and stuff like that. You know, don't work too hard to necessarily find zeros of polynomials if it's not easy to factor. You can graph whatever in y1, be it velocity, acceleration. You can graph 0 and y2 and find where they intersect. That's probably going to be the easiest way to find zeros for some of these, okay? But let's go through these problems. The ones I think we go through tend to factor pretty nicely, so not necessarily going to need the calculator for these, okay? But we'll do these together right now, and so let's see what's up. At number 1, an object moves along a coordinate line so that its position S satisfies S of t equals 2t squared minus 18t plus 8 for t values that are greater than or equal to 0, where S is in centimeters and t is in seconds. Okay, so position is measured in centimeters, just using this S of t function for that, and t is going to be measured in seconds. As we look through the questions, I'm just kind of looking ahead. It asks us about moving to the left, so we know that we're dealing with horizontal movement in this problem. Okay. Determine the velocity of the object when time is 1 in 6 seconds. Okay, so for part A, I'm just going to come down here where I have a little room. Let me rewrite that function. Position function is 2t squared minus 12t plus 8. On the domain, t greater than or equal to 0, which again kind of makes sense. We're talking about time here. All right, and in part A, we want to evaluate velocity at times 1 in 5. So to get the velocity, all we're going to do is take the first derivative here. There we have it, and now we can evaluate it at whatever moments in time we want. Time 1, it looks like we get negative 8 centimeters per second. And at time 8, 8 times 4 is 32, minus 12 is 20 centimeters per second. You want to make note of the units here. We do like to include units when we know what they are. Okay, so there we go. We've got velocity at times 1 and 6. Okay, part B, when is the velocity equal to 0? When is the velocity positive? When is the object moving to the left? That's going to be when velocity is negative, okay? So let's analyze velocity a little bit here, okay? So for part B, when is velocity 0? Positive, moving to the left. So let's set velocity equal to 0. So 4t minus 12 is 0. And with a little bit of effort, we get time 3 seconds here, okay? So the velocity equals 0 at time t equals 3 seconds. If this is an AP exam short response question, you want to be very precise and very clear. You want to take a couple seconds to write that out. Okay, you don't want to shortcut things. You want to be very precise. So v of t is 0 at time 3 seconds. What else do we got here? When is the velocity positive? Okay, so now what we're going to do is set up a number line test. All right, so we've got a number line that represents, let's see, the t value on the bottom and the velocity on top. We're on the interval 0 to infinity. And at time 3, the velocity is 0. So on the bottom are my t values. Up top is velocity. And now what I'm going to do is I'm going to pick a number less than 3 and greater than 0 to plug into velocity. And then I'll pick a number bigger than 3 to plug into velocity. So let's look at velocity at time 1. That's going to be, let's see, 4 minus 12 is negative 8. So that came back less than 0. That's really what I care about. That's an indication the particle is moving to the left here. So I'm going to draw that arrow in. Velocity at time 4, some number bigger than 3. 16 minus 12, that's positive. Velocity is positive. Particle's moving back to the right. Okay? And so, let's see, it asks when is velocity positive. V of t is greater than 0 on the open interval from 3 to infinity. And the particle is moving to the left on the interval 0, 3 because velocity is less than 0. Velocity is negative. And typically, again, on a short response type problem, you're going to have to justify your answers. So that's why I'm writing these justifications out, and I would ask that you do the same. Okay? That takes care of part B. Part C. How far does the object travel from time 0 to time 6? Okay, so again, distance traveled is the integral of the absolute value of velocity. From time A to B. And it's the absolute value. Displacement is the integral of velocity without absolute value. Okay, so you want to know the difference between the two. Total distance traveled versus displacement. For example, kind of go off on a tangent here. Like, let's suppose, hey, good morning. Let's suppose, like, when you come to school and you go back home, okay, you have a total distance. So you live exactly 1 mile away. You go to school, it's 1 mile. You come home, it's 1 mile. Your total distance traveled is 2 miles. Your displacement, on the other hand, is 0 miles. Okay, displacement is how far away you ended from where you started. So if you start at home, you come to school, you go back home, you ended up where you started. Okay, we'll talk a little bit more about that at another time, but just for now, understand the difference between the two. Okay, the two integrals. So for total distance, we need the absolute value of velocity, and in this case, we want the total distance traveled on what interval of time? 0 to 6. So we'll set up the integral from 0 to 6 of the absolute value of velocity, which in this case is 4t minus 12. Okay, and then this is where, you know, if you really want to do it out, you can do it out, but I would say just punch it into your calculator. So I'll go ahead and use the Math9 function here. 0 to 6. Okay, absolute value, you go math, and then to the right to number, and it's the first one there. It says ABS if you're using your calculator, and you get those absolute value bars. And just use the letter X on the calculator instead of the letter T. The calculator doesn't know the difference. Okay, and I am getting exactly 36, and again, the units were centimeters, so 36 centimeters of distance traveled. Okay? And part D, when is speed increasing? Okay, so to determine speed, we have to look at the signs of velocity and acceleration. All right, so determine speed. We're going to compare the signs of velocity and acceleration. Okay. So let's reiterate, velocity was 4t minus 12. And we already have this number line that we've looked at. And taking the derivative of velocity, we get acceleration, which is just the constant 4 here, okay? So look, that never equals 0. It's just a constant 4. And so the sign of acceleration is always positive here, okay? So if I was to make like a number line for acceleration, it's just always positive, okay? Now the idea is to try to compare where, on what intervals, the signs are the same or the opposite. And what I typically, it's not too hard to see here, but I like to try and put these into a single number line. So I do something like this, okay? Here's our number line starting at 0. I'm going to have a row for velocity and a row for acceleration. All right, and again, these are the time values down here. And now, anywhere I have anything like kind of important, I'm going to get it on here. So like time 3, the velocity was 0. It was negative to the left, positive to the right. So I put a bunch of minus signs and plus signs in there. What did we say about acceleration? It's always positive. So I'm going to put a bunch of plus signs through here. Speed is now comparing the signs. If the signs are opposite, speed is decreasing. Where the signs are the same, speed is increasing. And so, where is speed increasing? Speed is increasing on the interval from 3 to infinity because velocity and acceleration have the same signs. Okay? And then finally in part E, something a little different, draw a schematic representing the motion of the object. So what do we know about this thing, okay? Well, looking at the velocity of this, we know that it starts moving left for the first 3 seconds of travel. At time 3, it stops, it changes direction, and it goes back to the right indefinitely, okay? So how do we represent that? Basically, we have this object, this particle, it moves left for 3 seconds, and then it goes back to the right, okay? Well, we want to kind of show that. Okay, so here's what we're going to do. We're going to have a position number line to show the motion, and I'm just going to have position 0 there. Label this S for position. All right, and now some important positions to come up with. I would say our starting position is important. So I want S of 0. So I'm going to go back to my S function, plug 0 into this thing. It looks like we'll get back 8. So there's our initial position. We're starting at position 8. There's a dot, okay? Then I need the position anytime I change direction. Right, we change direction at time 3 here. So now I'm going to evaluate position at time 3. So let's see, 2 times 3 squared. What do we get here? 9 is 18 minus 36 is negative 18 plus 8 is negative 10. And so we are at position negative 10 at time 3. So I'm 10 units, 10 centimeters to the left of 0 at time 3. All right. What else do we know? We know that just looking at this velocity thing, we're moving to the left from time 0 to 3. Does that make sense with our dots? Yes, it does. So this is time 0. This is time 3. We label those. And which way did we travel? We traveled to the left on that interval. Then what happens at time 3? We momentarily stop, we change direction, and we head back to the right indefinitely. So how do I draw that? I just go like this, and now I draw an arrow back to the right. In reality, imagine this, your particle's right here. It goes 1, 2, 3, and now it's going back to the right indefinitely. Okay, and this is how we show that. It doesn't go up or down at all. This is just how we show that, look, from time 0 to 3, we're going to the left, and now we're going back to the right. All right, and that's the gist. All right, let's try another one, and then you guys give the homework problems a try. And again, don't hesitate to use your calculators where you need to, okay? Number 2, here's this position function, t cubed minus 9t squared plus 24t. Morning. Minus 9t squared plus 24t. And again, t greater than or equal to 0. All right. In part A, when is position increasing and decreasing? Okay. So again, when is a function increasing, decreasing? When its derivative is positive or negative. All right, so we got to look at the first derivative position to determine where it's increasing and decreasing. In other words, we're going to look at velocity. Okay, and so let's see, we can factor that. We can refactor this. And there we have it. So looks like velocity is 0 at times 2 and 4. And now I'm going to look at the signs in each of these regions. So let's suppose we can plug 0 in. If I plug 0 into velocity, I'm going to use the factored form. We get 3 is positive. We get negative times negative is a positive. We're moving to the right, which is where position is increasing. If I plug a number between 2 and 4 and like 3, we get a positive 3 out front. 3 minus 2 is positive. 3 minus 4 is negative. That's a negative product. We're moving back to the left. Position is decreasing. Plugging any number bigger than 4 in, all of these factors will be positive. So we're moving back to the right, and position is increasing. So to formalize the answer, S is increasing on the interval 0 to 2 and 4 to infinity because velocity is positive. S is decreasing on 2, 4 because velocity is less than 0. Okay? All right, so part A done. Let's take a look at part B. When is the velocity increasing or decreasing? Same idea of function increases and decreases when its derivative is positive and negative. So we got to see where acceleration is positive and negative. And let's change the color up. Okay, taking the derivative of velocity, 6t minus 18. Setting that equal to 0, we get t equals 3. Same idea, test the sign of this around 3. Okay, plugging a number less than 3 into acceleration, that's going to be negative. So velocity is decreasing. Plugging a number bigger than 3 into acceleration is going to be positive. Velocity is increasing. So velocity is decreasing on 0, 3 because acceleration is negative. Velocity is increasing on 3 infinity because acceleration is positive. Okay. I believe in part C, they're going to ask now, when is speed increasing or decreasing? And this is where we got to be a little more careful, okay? Indeed, that is it. When is speed increasing, decreasing? This is kind of the odd man out, if you will, in that this is the one where we have to now compare the signs of velocity and acceleration. Okay, and we don't have to work too hard for that. We've got both these number lines right up here, okay? And again, I'm going to kind of put them together in a single number line, and we have 2, 4, and 3 as our zeros. Okay, and we'll have a velocity and an acceleration. Velocity was 0 at 2 and 4. That went positive, negative, positive. Acceleration 0 at time 3, that went negative, positive. Right, and now in each interval we can pretty clearly compare the signs for speed. Opposite signs, speed decreasing. Same signs, speed increasing. Opposite, same. All right, so speed is decreasing on 0, 2, and 3, 4 because that's where acceleration and velocity have opposite signs. Speed would be increasing on 2, 3, and 4 infinity because acceleration and velocity have the same signs. Okay? Part D. Find the total distance in the first 5 seconds. Okay, so we're going to integrate the absolute value of velocity from 0 to 5. And what is velocity? There it is. 3t squared minus 18t plus 24. Okay, so there's your integral setup. And once again, take a moment to punch that in. I'll do it as well. Math 9, integral 0 to 5. Math number absolute value, 3x squared minus 18x plus 24 dx. And it sometimes takes a couple seconds for this to go through the calculator. So don't be surprised if it feels like you're waiting a moment. And I'm getting 27.9999, and we'll call that 28 to the nearest thousandth. Okay, so 28 units of travel over the first 5 seconds. And part E, again, draw the schematic. Okay, so again, we want the initial position, and we want the position at any direction change. Direction changes, we see signs of velocity change at time 2 and 4. Okay, going back to the position function here, if I plug 0 in, I get 0. If we plug 2 in, oh, pardon me, time for the pledge, so bear with me for a couple seconds.
I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Today's motivational quote is simply, keep going. There's no telling what the future might hold, but you gotta keep pushing. Today's day 1. Have a fantastic Thursday. Oh, today's the day 4.
All right, back at this, just to wrap this up, position at time 2 was 20. I just plugged it into the calculator, and position at time 4 is 16. Okay, so this is really all we need to draw the schematic. Here's our number line, label it S. There's 0. At time 0, we're at position 0, so a dot right there. Again, just let's take a look. Velocity is positive from 0 to 2, so we're moving to the right. At time 2, we're at position 20. That seems to make sense. We went to the right. And again, somewhere off on the side, we label these time values. Okay, now at time 2, we stop and change direction. We're heading back to the left until we get to position 16. So I'll do this, and I'll do that to indicate that, and that was at time 4, at which point we stopped, we changed direction, and we head back to the right indefinitely, okay? We were going to the right, we were on the left from time 2 to 4, now we're going back to the right. And so I'll do another one of these and indicate that. And there you have it. Again, represents, okay, 1, 2 count, 1, 2 count, and then back to the right. All right, folks, so try those problems. If you have any questions, reach out, and have a good day.